In this video, we're going to be discussing Voronoi graph planning. We're going to introduce the concept of Voronoi graphs. We're going to discuss planning over a Voronoi graph using particle obstacles, and we'll then extend planning to normal obstacles. And this is just a really great example of generating a graph and using graph search techniques to help us find our path to the goal. So let's go ahead and get started. So what you'll notice here, oops, I didn't mean to leave that in there. We have a series of points. Each one of these black dots is an obstacle. Now to these lines that are drawn here, these are lines that separate, that have points that are equidistant to each obstacle. So if I were to choose a point right here, and I draw a line between this obstacle and that obstacle, those lines should be exactly the same length. Intersections of these lines, so if I go right there, intersections of the lines are going to be equidistant to multiple points. So we have 2, and we have our third point right there. So we can then define this structure, which helps us, we can navigate and stay away, as far away from obstacles as we can. So say we're trying to go from point A to point B, we can use these lines or these edges to help us decide exactly where to go so we can stay as far away from obstacles as possible. So we could search over here, maybe we'll go follow these points. We'll end up following this path from point A to point B. Okay, so that's the basic idea of this Voronoi graph. As we look at this, for a finite number of Q points, so again, now I'm looking at the text, but those black points that are now all colored in a different color, right? We can define what's known as a Voronoi graph. So we've divided everything up, and each one of these cells is a convex cell, convex region where every point in that region is closest to the black point that it contains. So we'll generate a graph from this where edges of the graph are the black lines. So we'll generate the graph from those black lines, and the vertices are going to be the intersection points. Okay, so here's another example. So this one's generated with 20 points. You'll see here that we do have some places where obstacles are very close, so perhaps this line might not be super desirable, but still, if we're going to end up going through this environment, if we stay on the lines, we'll be staying away from obstacles as far as possible. Okay, so we can generate it with any number of points, and these lines that typically go to infinity can obviously be bounded by a bounding box. Okay, so we're going to then, like I mentioned, we're going to design a graph based on this structure. So each one of these blue dots, these intersections of the points, these blue dots are going to be our vertices of a graph. And each one of these red lines, right, that connects the vertices, these are going to be edges, and there's a tiny little one in there. So these lines are going to be our edge set. And these are two different sets. We'll denote the vertex set by V and the edge set by the letter E. But either way, we can come in here, once we've have a bunch of obstacles, at this point they're just points, we can now define this graph where we have vertices are particular positions and edges are transitions between positions that stay as far away from obstacles as possible. So that's the definition of our Voronoi graph. What we will want to do is we will want to add a start and an end position. So here's our position start and here's our position end. We'll want to connect that. This suggests to the 3 closest graph nodes. Now that's just that's a choice. And by nodes and vertices, we're going to use synonymously. So you'll see here that we have our endpoint would connect it to the 3 closest points here or any whatever number you end up choosing, we'll end up connecting the starting point similarly to the graph as such. So now we have the starting and end nodes are joined in with our vertex set. And then we'll add in also the edges. So we add in the vertices corresponding to starting and end node, and then we add those edges. We'll then search to find whatever the best path is, and we'll talk about that. And that best is something that we get to choose, right? Is it going to be the shortest, the furthest from obstacles, or what? And the book provides examples for distance, for calculating, for a metric on proximity to obstacles. Okay. But it could actually be any metric that you choose, as long as we can assign some sort of a cost with the path that we're traversing. So we'll go in and we'll calculate a cost, and this is what I was just mentioning is in the book, where it talks about being able to define a metric based on the distance to an obstacle. And then we'll come up with a cost assigned with each edge. Now each edge, if we look here, each edge, so let's look at, these are two vertices 1 and vertex 2. The edge consists of just these two vertices, right? So for each one of these edges, and right here we see a whole bunch of edges, right? All of these different edges, so we could do edge 1, edge 2, edge 3, edge 4, edge 5. Anyway, for each edge that we define, we need to define what the cost of that edge is. So that's going to be our path cost. So a common cost is going to be the edge length. So that would be just the distance between our two vertices. And then in the book, it also talks about adding in potentially a reciprocal of the distance to the closest point. So this would help us avoid getting too close to obstacles. And for example, this edge right here might be a poor choice, right? Because it's going right next to a couple of obstacles. Another way to do this would be to just look at obstacles, and look at paths, and if they run too close to an obstacle, then maybe we just remove that edge and we don't have to worry about that cost at all. Regardless, we can keep it or not. And K1 and K2 I'm going to put non-negative, meaning we don't have to have both of those terms. But for this example of our cost, this K1 and K2 provide a trade-off between how the length of our path and the distance to the obstacle. Okay, so now we'll jump in and look at the planning algorithm. So we're going to have, again, we're just considering obstacles as a bunch of points. So our input is a bunch of obstacles in that set Q, our starting position and our ending position. So as we come in here, we'll first initialize our graph with the Voronoi graph using Q. And again, V is the vertex set / node set. And E is the edge set. And E is going to be a subset of V cross V. So in other words, each element of V is just a tuple that has two vertices. Okay, then what we're going to do is we add in the start and end points. And at this point, after line 2, they're in our vertex set, but we don't have any way to get from the start point to the end point because there's no edges connecting them. Okay, then for each of our start and our end points, we're basically augmenting our edge set, right? And that would be these 3 lines. So in this case, these 2 lines, I should say, these augment our edge set. They connect start and end points, PS and PE, to the graph. Now we have to go through and we have to assign a cost to each edge. So we have for every edge, so again we have 2 vertices in an edge. For every vertex edge in E, we're going to assign a cost. So this is the cost to get to traverse from A to B. And this is what we do according to, this is that equation. Okay, so up to here, this is just constructing a graph. And then what we can do is we can say, hey, let's search our graph, and this is our find a path. So we're going to use a Dijkstra search. A Dijkstra is just a cost wavefront approach to traversing through the graph. We can use any other numbers. We could use variations of Dijkstra like A star, and we could even use breadth first or depth first searches, and they all have certain properties that are desirable, but Dijkstra or A star at least is trying to find the lowest cost path. Okay, another thing that we can note is that these algorithms are commonly available. So for example, it gives MATLAB, we can use Voronoi or shortest path functions, and in other languages there's similar tools, right? So these are very common constructs. But either way, we construct a graph and then we search it. Now there's a whole host of variations on constructing this graph, right? So we can construct different types of graphs. We can construct visibility graphs. We can construct grid-based graphs. Anyway, we can take any number of ways to construct a graph, and then this Dijkstra search, we can do a whole host of ways to find a path. Right? So this is a representative approach for a graph search technique. Okay, so here's a couple examples. So again, we had those 20-point obstacles. We had our start and our end, and then we found the path through it. So we'll be taking all of these edges through the graph. So there you have it. There we have our first path planning capability. So we really quickly want to adjust for having something that's not a point obstacle, because most of our obstacles aren't points, for example. So we have to ask ourselves, how do we handle solid obstacles? A point obstacle is just the center of the obstacle. It won't provide safe paths. So if we were just trying to say, hey, can we do that? We might do okay, but this path going between those 2 points might have a collision. Right? So that's not a very good approach. But what we can do is we can look at all the vertices of these edges, or all of the boundaries. Right? And so what we're going to do is we're going to just draw things on the vertex, on the boundary. So we add points on the boundary. Or if the obstacle is small, then we can just treat it as a point. So there may be obstacles that are small enough that we can just treat as a point. And we might have weird shaped obstacles, right? So we just have to add enough points along the edge of that obstacle to make sure that we're characterizing that obstacle pretty well. So what we're doing is we're fitting a polynomial, a polygon to our obstacles. And in this case below, the obstacles are defined as polygons. Okay, so that's our first step, is we're just going to start to define basically our obstacle points as the vertices of the boundaries of our obstacles. So in here we insert points around the perimeter, and note that I had only done it as on the edges, or on the vertices, but you'd probably want to have some on the edges as well, right? Or you could. And then the one problem though is once you've constructed the Voronoi graph, you're going to have a bunch of the possible edges are going through, right? And so remember, our graph we were constructing as the intersection. Our vertex set was the intersection of all of these different paths, right? So we have a whole bunch of points that are inside obstacles, and we just have points or paths that are going into the obstacles themselves, right? So that's somewhat undesirable. So we have a lot of infeasible edges that go into the obstacle, and those aren't paths that we want to take. So what we'll do is we'll just remove anything that goes into an obstacle. And so once we remove the infeasible paths, right, then we're not going to be going inside of an obstacle. And then so we take our graph, we form our, let's kind of review. So we take our obstacles, we add points to those obstacles along the boundary. We then form our Voronoi graph as if those points are just the obstacles themselves. And then the final thing we do is we just remove any of those possible edges that were going into an obstacle. We just say, hey, that's not a possible edge. And then we have now we have a graph that we can follow that'll produce desirable paths. There you have it. So that's our Voronoi graph planning.